All right. I've been talking a little bit about basics of Linux. Now let's start to get slightly theoretical so we can actually do some analysis of our programs. The whole point of data structures is to store your data efficiently so that your programs will run actually faster. High performance is what we're going towards. But before we talk about what improves performance, we need to at least come up with some groundwork in order to do the analysis. How do we actually gauge one program is faster than another? So we're going to talk about that, and which is Big O, or complexity analysis. Those are the first two things. We're going to do some practice because Big O, for a lot of people, is going to be confusing at first, but it's actually really simple. It's simplified, I'll put it that way, than what it could be if we were doing a full math course here. And then we're going to talk about gprof and GNUplot, which are tools to help us actually do timings and figure out how to improve performance and get the timings. And then we'll talk about more timings and some tips I can give you. All right. The dilemma when you're doing an analysis of algorithms is you may have two or more methods to solve a problem. How do you figure out which one is best? How would you do it? You have two methods. What determines what's the best method to use? Least lines of code. That's always a good one. That is a solid first answer, and that's actually the one you should gravitate towards when you go into the workforce. It's least lines of code. But what happens when that least lines of code one is too slow, and you have three other ones that are, I'll just say, complex lines of code, but they're all equally complex? And that does happen, by the way. You should gravitate towards the simplest one first, and if that doesn't work, then you need to choose another one. But let's say you did a little research and it appears like there's three solutions. How do you figure out which of those three are the better or the best?
Look up their Big O.
Look up their You're cheating. Cheater. Anyone?
One that runs the fastest.
One that runs the fastest. So how would you determine which one runs the fastest?
You gotta use when you're about there.
Use when we're about ready to learn. Well, right. So you can either inspect the algorithm and try and decipher from inspection, or you can run it and figure out which one actually runs faster. Which of those two methods are better? Depends, actually, because if you have a program that's going to take weeks to complete, you may not want to try and run both of them and figure out which one's better. You're going to want to stick with an analysis first. On the other hand, if you just need to run it real fast, just run it real fast. Okay. So what did I talk about over here? Implement the algorithm in C, test how long it takes to run. Well, if it takes weeks, that may not be a good idea. Step one, well, you can characterize the performance in terms of key operations. So when you start talking about doing analysis from a theoretical standpoint, you need to pick what you're going to do the analysis on, what operation. For example, if you're sorting, you need to count the number of times two values are compared, because you're comparing two things. And you're also going to count the number of times two values are swapped, because in sorting, those are the two main operations, comparing and then swapping things around. Is that clear? Sorting, hopefully that didn't take. Y'all did some sorting in procedural or not yet? That's a good question. No sorting?
Did a little bit.
I mean, you did it in this class, data structures. Okay. But no sorting yet? That's fine. Search, count the number of times the value's been searched for and are compared in the array. So notice in sorting you have compare and swap, search you have compare, and the recursion, probably the number of recursive calls, since that's the expensive operation. In general, we want to talk about general performance. Empirical measures for several examples, but doesn't tell us. But what does this tell us in general? Well, it may tell us things in general, or it may not. Oh, and I wish I had my camera so I can explain this. To the person online, sorry, online student, you don't get to see this. Or maybe no one gets to look at your part. We're going to come up with a graph. But I'm going to give you a little precursor here about why empirical may not be the most useful. If you're doing a quadratic function something is quadratic in performance, it may look something like that. Okay? If your empirical data only shows you from here to here, it may look linear. Right? In actuality, if it goes from here to here, it may look linear as well. So the empirical search will probably need to go from here all the way up to here in order for it to actually tell you, oh, hey, look, it looks quadratic in nature. So that's why an analytical assessment is usually better, because it'll give you instead what the full curve looks like. And how do we do it? Well, how many comparisons for a size of n? So this might be size of n, and this is time, usually in seconds. Okay? It may be difficult to discover a reasonable formula. Hopefully that's going to be intuitive. If not, it will be soon. Analysis of the varying results. So for some sorting algorithms, sorting routine may require n-1 comparisons and as many as n squared. We haven't talked about different sorting algorithms, but there are sorting algorithms that have variable number of comparisons depending on your input. It's totally data driven. So that's why we talk about best case. Well, what's the fastest you can run a program in? So an optimal situation, well, it'd be n-1. What's the worst case? Well, it's probably n squared over 2. And then what's the average case? Maybe something in between. All right, starting to throw these math formulas out at you, so let me explain what this means. Excuse me, given an algorithm or sorting algorithm and an array of size n, so n number of integers to sort, in best case it only requires n-1 comparisons, and at worst case it requires n squared over 2 comparisons. Does that make sense what I'm saying? So we're trying to, those are the best case, those are the worst case, and then maybe the average is somewhere in between. We'd have to do an analysis to figure out what the average case would be. Usually we look at the worst case. A very common exception is if the worst case is a rare case, in which in that situation we would look at the average case. Is that clear? Questions? We are estimating. We are not going to give an exact answer. We are trying to estimate the correct number. If you were to run this empirically, your empirical numbers will be off, but they should be close because we're giving a good estimate. Estimation is an important skill. Let me give you a good example I like from last time. How many hot dogs tall is the Empire State Building? 4,000.
4,000 hot dogs. It's probably like, what, 2,000 feet tall?
Oh, well, that was good.
Probably a hot dog's like 6 inches. So.
Man, you're on top of the ball. So first we asked the simpler question, how tall is the Empire State Building, for doing an actual analysis. It turns out to be 1,250. You weren't that far off, actually.
Yeah.
I mean, yeah, that's actually pretty good. And then a hot dog 6 inches from end to end. Nice. Good job. You've eaten a lot of hot dogs, haven't you?
No, I
So we would multiply the two, and we would estimate that it's 2,500 hot dogs. If we actually tried to run a string of hot dogs from the top to the bottom, it might be more, it might be less, depending on how we strung it together and whatnot. But we would be pretty confident it'd be close to 2,500 hot dogs.
We could take a field trip and
Yeah, it's just a,
It definitely a field trip time?
Yeah.
Okay, I think it's time to test it. I'll go tell us.
CSU will pay for it, I'm pretty sure.
Oh yeah, because CSU pays for everything. All right, this is the idea, guys. We have an algorithm. What do we expect it to do? We're giving an estimation. So that's what complexity analysis is, an objective way to evaluate the cost of an algorithm. It's usually done in terms of space or time. We talked about seconds, but it can also be space complexity. Given a size, well, sorting of n integers, maybe your algorithm requires n squared memory in order to do it, but can do it really fast if you consume a lot of memory. That can also happen, and that'll make sense later on. But we need to have a meaningful way to compare algorithms on a common measure. It has two phases. Usually you do algorithm analysis, try and figure out what the algorithm's doing, and then you do actually the complexity analysis, how complex or what is its speed. All right, algorithm analysis. Unfortunately, or maybe fortunately, depending on how you look at it, there is no generally accepted set of rules for algorithm analysis. So I can't just tell you what you need to do in order to do analysis of this algorithm. The reason why that's a good thing is that means you now have a job, because the computer can't automate this for you. Or if it could, it does a very poor job. In some cases, an exact count of operations is desired, and others, general approximation is sufficient. What I'm going to show you are very common rules that you can use for this course in order to give an actual correct big O or estimation. All right. Step one, we assume an arbitrary time unit. This is the best assumption ever. This is not real life, but this is going to make everything you do easier. We're just going to assume everything takes the same amount of time. aka an addition, a subtraction, a division, a comparison, a multiplication, a function call all take the same amount of time. I'll tell you right now that is definitely not the case. But for the time being, we're just going to assume that they all take the same amount of time, because that's going to simplify all of our estimation. Remember, we're just doing an estimate right now, so we're just trying to get something that makes sense. When you get into more advanced analysis of algorithms, especially in architecture, yeah, we'll talk about how division takes 20 to 40 times as long as an addition, but that doesn't matter right now. So it takes one thing to do an assignment, one to do an IO operation, which is really slow, one to do a single Boolean operation or a numeric comparison, a single arithmetic is one, a function return is one, and going into a subscript of an array is one. Everything's just one. All right. Running time of a selection statement, aka an if or a switch, is the condition that you have to evaluate. So if your if statement has an and in it, that's a time unit of 1, but if it has an and an or, it's a time unit of 2. Plus the maximum running time of the individual clauses in the selection, aka how long does everything take to run inside of the if statement. A loop, the time is the sum over the number of times the loop is executed of the body plus the time the loop check and update operations. All right, so in the loop, you have that if statement that you always run, so you have to add that, and you multiply that by how many times the loop is executed, and then you're going to also add the number of times, the body of the loop times the number of times it was executed. We're going to do examples, so that should make some sense, better sense soon. Always assume the loop executes the maximum number of iterations. Running time is 1 for a function is 1 for setup plus the time of any parameter calculations. All right, let's start with something easy. Count equals count plus 1. That's the cost of C1. And sum equals sum plus count. Since we assume plus cost 1 and assignment cost 1, the total is 4. Why is the total 4?
So you're adding it, then you're assigning it, so that each count is 2.
That's 2. 4. Because you have 2 additions and 2 assignments. So we're saying that this cost 4. Whatever. Time units. We don't care. It cost 4. What was it?
Schmeckles.
Schmeckles. All right. How about this? Another example. Okay, so we'll talk. I gave this one out. If statement, that's fine. So the if statement has a cost of 1 because it has a less than. So that cost, aka C1, is 1 because there's just one comparison. Cost of C2 is actually 2 because you have to negate something. That costs 1, and then you have to assign it. So that costs another 1. The cost of C3 is 1 because we're just assigning something. So the worst case of this whole if statement is a cost of 3. The best case is a cost of 2, and then the average is 2.5. Notice that the cost is not 4. We're not adding everything because only one if of the if statement is going to execute and not the other. And this actually is a good example when you would do average case, because over the run of, I don't know, 1,000 times, chances are it'd be about 2.5. Any questions? All right, here we go. Now, let's do this example. Please tell me I do this one at a time. Yes. What's the cost of C1? Cost of C2? Cost of C3? 1. Because I'm just asking what's the cost of, the comparison. What's the cost of C4? Ooh, that could have been funny if taken out of context. Yeah.
$2,500.
And what's the cost of C5?
2.
All right. All right, so those cost values are just of that line. What did I say next? How many times does a loop execute? N times. Perfect. Loop n times. So total cost of this whole piece of code is what?
4n plus 2.
We got 4n. Well, actually, all right. Well, what's the setup cost before the while loop begins? 2, because it's C1 plus C2. So it's 2 plus 4 times, or I'm sorry, n times. Actually, it's n plus 1 times C3. Why is it n plus 1 times C3? Well, before we go to C3, let's go talk about C4. Why is it n times C4?
Because you've only done it once.
Well, how many times is C4 called or executed? N times. So it's n times C4. How many times is C5 executed? N times. Why is C3 n plus 1?
You're doing it at least once before you start doing it 10 times.
Close, other side. You have to check if that one last check in order to know to exit the loop. So C3 is actually n plus 1 because the while loop executes n times, but on that last iteration, it still has to do the comparison to know to jump out. Is that clear? All right. Hey, let's do another one. What's C1? What's C2? What's C3? You know we're doing great. C4? C5? C6? All right. C7? And C8. All right, let's see if we did that all right. Perfect. All right. First, our outer loop executed n times, right? Okay. Second inner loop is executed n times as well. So what's the total cost? Who wants to write the formula? No one? No one?
All right.
You want to? Okay. Yeah, wherever you want to write it. I'll give you an eraser.
Like erasers?
Yeah, go ahead.
I know you start with n squared because it's a double for loop.
I think you're jumping ahead.
I am.
Yeah, erase. Good start. Start at the beginning. What's the setup cost?
The setup cost. We're starting from C1, right?
Yep.
Okay. That's plus 1.
All right.
And then the next one is plus 1. C2 is plus 1.
All right. Write this out as a one long formula. So it'd be 1 plus 1.
Okay. Gotcha. 1 plus 1.
All right. Now, What's the outer loop is executed how many times?
The outer n times.
All right, so let's do plus in,
Plus n.
and then open parentheses. What's in here?
The cost of everything else inside the outer loop,
All right, so you got C4.
which is
Yeah.
1. And then
Okay, yeah. Sorry.
then you have the while loop, which
Alright.
is another.
So plus in, well, plus in, because now you got another while loop.
Okay. Plus
Open parentheses. So it's actually not that bad if you just write it all out.
Okay.
And then plus, and then inside of that, oh no, in. You want the parentheses over here.
I close the parentheses.
No, open it.
Make another open parenthesis.
They're open. Open parentheses.
I'm slightly confused.
All right, because what's going on, like, yeah, you're confused because you're right at the board.
Okay.
It always happens. It makes way more sense when you're sitting out here, trust me.
Okay.
So you have the 2 at top, right? That's 1 plus 1. And then this is going to execute n times. Now we forgot to do C3, but that's okay. We'll get to that in a moment. C4, which is that 1, inside of that in parentheses, because notice n is going to be this whole thing right here,
Okay.
right? So we have that 1 right there. Now we're going to have another n. So that's where we're starting another n with the parentheses. And we're going to go ahead and skip C5 for now. But we're going to have, what's here? C2,
That's 2.
all right?
So I put 2.
2. And then another plus 2. Now we're done with that n because this loop ends. So close parentheses. And now we're going to add, whoa, just 1, because we're just done with that loop. We're still inside the outer loop, so we need to add the cost of C8.
2.
Yeah. And now we're done with this loop, so we can end that. Now we did forget to add C3 and C5, but that's okay. I wanted to show you how this formula was actually not that hard to derive. Thank you.
Yep.
And now I can put this. And actually, if you just want to add C3 real quick, what's C3? We got, that'll be n plus 1 times C3, which is 1. And then we also, inside here, you're going to have n plus 1 times 1 again for C5. All right. Vroom! If you actually multiply all that out, it looks something like this. Notice how I got all the constants on the left, then n times all those, C3, C4, C5, C6, C8, and then n times n, C5, C6, C7. Okay? If I'm asking for full complexity analysis, this is what I'm asking for. All right? If I'm asking for full complexity analysis, that is what I'm asking for. Let me go and pause the recording.